Hello, everybody. I'm Andrei, and I work for JetBrains as a Senior Vice President of Investments, Research, and Education. Welcome to Regionals. Great things happen when great minds come together. JetBrains wants to seek out great minds all across the globe, support their initiatives, and work together to create great things that will make the world a better place. That's why JetBrains is proud to be a Global Tools sponsor of the ICPC. There are already many great minds working at JetBrains, and together we have created some amazing things, like the Kotlin programming language, for example. It keeps on growing and growing in popularity. In 2017, Google began officially supporting Kotlin as a language for writing Android applications. We have also created professional development tools like Cline for C++ programmers, IntelliJ IDEA for Java, PyCharm for Python, and also educational tools that help people learn and teach programming. The regionals are the biggest contest in the ICPC calendar. Thousands of talented people all over the world team up to solve complex real world challenges. These contests are the proving ground for future champions. But even if you don't make it through to the finals, the experience of competing in the regionals and the new friends you'll make along the way are priceless. Enjoy the ride. Best of luck to everyone.
We had a simple uh, version of this problem which was proposed, which had, I think, only one condition. But later, Udit came up with let's add one more factor that we can select at most k nodes. And yeah, many testers said that this is very common idea, and like both of the problems separately exist somewhere. And we thought that, yeah, if everyone is complaining about it, it's better to use in online round. But sadly, it was not that easy. So now I would hand over to Udit to explain the solution. Udit, you there?
Yes. Am I audible?
Yeah.
Yes. So the problem was that you're given a tree. You can select at max k nodes from the tree such that the pairwise distance between any two nodes is at least h. Um, and you have to maximize the values of the values at the node, sum of values at the nodes. So the first natural thing to do would be to root the tree, and then we'll do a DP on the tree. So we define a DP IHK, which is consider the subtree of the node I, and we'll be picking at max k nodes from the tree, and the closest node from the node I should be at least at a distance of h. So in this, we can do a O of h square times k square times number of children merge. I'll show the code in the next slide. Um, uh, so this is basically O of n to the power 5, which is very slow. So next slide. It can be improved a little bit. So uh, we can do several improvements in the inequalities to get instead of O of n to the power 5, we can do O of n to the power 4. Can you show the next slide? So this was the brute n to the power 5 code. This is we are doing just a DFS and doing the standard DP on tree merging. So this is the main part, Remax DP, this thing. First, we are iterating over the current minimum depth, then the current number of nodes, then the next the height the depth will be taken from the new children subtree, and then the number of nodes will be taken there. So it will be the current. I mean, you can see the recurrence. If you spend some time to think about it, then you'll get it. So here, this code is n to the power 5, but we can do a few improvements to this. First of all, we can observe that we don't need to iterate over this IV variable, it's enough to just consider two values of it. One is the case where IV will be the new minimum, and one is the case where the current minimum will stay the minimum width. So uh, another improvement we can do is, instead of iterating from 0 to k, we can iterate from 0 to k comma subtree size, because we can't take more than subtree number of nodes. So with these observations, I think you can get n to the power 4 easily, or maybe even n cube. So next slide. Yeah, so also apart from n cube and n power 4, if you do some particular sets of inequalities, you also get n hk times min of h comma k. I think Kevin got this solution first, so uh, this is in reference to that. The next this slide is, so first we have two observations now. First observation is the value of h into k is not that large. So this is a little intuitive. So if all the nodes are at h depth apart, obviously you can't take a lot of nodes. So we'll be showing that you can only take at max 2n by h nodes. And the worst case is where there's a center and there's chains of length h by 2. So all the n nodes you'll be able to do take. So 2n by h nodes you can take. So we can assume that hk is of the order n, and using this we can also see that min of h comma k is of the order root n. So this O of nhk, min h comma k, can become O of n to the power 2.5. So this still doesn't completely pass, so we'll have to think of better solution. Next. The proof of the first observation is that consider any node we are taking and mark all the h by 2, all the nodes which are at a distance strictly less than h by 2 to it. So you can observe that no node will be marked twice, and at each step we'll be marking at least h by 2 nodes, a seal of h by 2 nodes. So the total number of nodes taken is 2n by h. There's one case where we won't be marking h by 2 nodes because the distance is already less than the total number of nodes is already less than h by 2. So in that case, we only mark one node. So it's max of 1 comma 2n by h. Yeah, next. Okay, so now the next observation is that in the first recurrence we were doing min of k comma subtree size. Instead of that, we can do min of k comma subtree size by h. Min of k comma 2 into subtree size by h. So because of the observation 1, we can see that this is enough number of nodes. This is the max number of nodes we can take in that subtree. So just iterating from 0 to the new k is enough. So for the proof why these limits are now enough, we can first prove for a binary tree. So the recurrence currently takes O of h times the subtree. So the recurrence currently takes you h times subtree size of left subtree by h times subtree size of right subtree by h. So that's less than equal to subtree size L times subtree size R. So the worst case recurrence will be the time taken to compute for the left subtree plus the time taken to compute for the right subtree plus the product of the subtree sizes. So, and for generalizing this to non-binary case, we can just add an auxiliary node with zero distance and just connect the new nodes to it. So this is a standard trick where just let me basically if you have 3 nodes, so connect the first one, then add an auxiliary node and connect second and third to it. So you can generalize this to non-binary as well. Next slide. Yeah, so this is the inductive visual proof for the case that this is at max n square. So we can inductively show that t of I is less than equal to half of I square, and then using this we can show inductively that um, this remains half of I square at all times. So another way to visualize this would be that the size of L times size of R, each pair of nodes is getting considered at max one time. So, and that point at which it will be considered will be the LC of both the nodes. So that's another way to look at it. Next slide. So this was the new code. This KU is basically min of k comma cur by h, 2 cur by h. So, and similarly KB, and this we are doing the same DP. In this we are not iterating over h again, just considering the two values which we needed to consider. So this was the idea.